Okay, let's get started. One of the people could hear the conversation that happens before the camera comes on. To like these kids. Okay. Where were we? Implicit differentiation. We looked at how to do it last time. Let's just actually continue with some examples, and then I want to talk about another differentiation technique. Okay. So last time we found y prime for this expression. Right? This was the poem of Descartes. Here's a follow-up to that. Find the equation of the tangent line to the above at the point 2, 1. So, as you can see here, if I were to plug in x equals 2 and y equals 1, I would get 4 minus 2, which is 2, plus 1, which is 3. So this point is actually on that curve, and I'd like to find the equation of the tangent line at that point. How would you go about doing that? How do you find the equation of the tangent line?
You can find the slope using what we
Right.
found for y
So
prime.
first, we know the slope is given by, well, y prime evaluated at the point. Y prime was, what did we have?
Negative 2x over 7y to the 6th minus 2,
The negative was on top.
I think. You can check.
Yeah.
Yeah.
So at this point, that means we can plug in x equals 2, y equals 1, and we can find that that would give us what? Minus 4 over 5?
Yep.
And so now we can use y minus y1 equals mx minus x1. Y minus 1 equals m x minus 2. That would be the equation of the tangent. So last time we saw this curve had a weird graph, wasn't even a function, something like this. And so basically we just asked for the tangent line to be around here, I think. Now, as I said, examining this function on its own is pretty complicated because you can't even solve for the y value. And we also saw that a tangent line allows us to approximate what a curve is doing locally. And so what calculus gave us the power to do here is, in the event that working with the function itself is too hard, what we can do is at a particular point of interest, we can draw tangent lines there. And essentially we can study this function in this region locally by studying that straight line. Working with this function is going to be a lot easier than working with that function, because this function we can't even solve for the y value. Now, you might worry, well, if we can't even solve for the y value, how can we kind of determine what points are there? Well, that's a matter of a different field of mathematics, like numerical analysis is where you figure that out. Sometimes you want to approximate coordinates on a function when you can't actually find those coordinates analytically. So here, it's kind of easy to see that 2 and 1 will work. Can we find all points on there? Well, we'd use some sort of approximation technique. So we'll say, okay, I care about when x equals 5. And so we'll plug in 5 for the x value, and we'll kind of approximate the solutions to the y value, right? And as we said with approximations, we just need to be accurate within a certain number of decimal places, which we have pretty good methods to get that accuracy. So ultimately, you might have a function that is quite complicated in the sense that you can't solve for things the way you'd want to solve for them. However, you can approximate coordinates on that function, and locally, you can actually analyze that function using tangent lines. So this gets us, this is one of the most common uses of calculus, is to really deal with issues like this. If we know that a function is differentiable, we can actually use calculus to analyze that function in ways that we couldn't have done before, which is, it's pretty cool. Let's actually go to some other computational examples. And then I want to talk about a different technique, differentiation technique. So these are just to get used to the processes again. So let's say here, and again, find y prime. Just want you guys to remember what we actually spoke about last week. Let's say that's a function that we care about, e to the x plus y squared. And c look at those examples. Does that last equation look familiar? No? Maybe? Does it? It actually looks familiar? What is it?
I don't know, but it does.
I've seen so many equations with p's and v's, so yeah, that's probably familiar. I've probably seen it somewhere. That's actually a result from chemistry. This is van der Waals equation.
Oh, it just looks really strange. Okay.
For a specific gas. So, chemists in a lab, probably inhaling ammonia gas, came up with this equation when studying without gloves. In this case, the P is actually the pressure of the specific gas, and the V is the volume. So basically, this was a rule they came up with in chemistry, and when it was derived, it came out like this, right? So you didn't have like one thing being solved for in terms of the other. It came as an implicitly defined function, where your pressure and your volume there kind of share this weird relationship, where they're kind of jumbled together. And this is like, I don't know if they couldn't come up with it in a different way, but this is actually the equation. Okay? So this was just an example to show you that things like this actually happen all the time. There are times when we're studying something and the relationship that evolves isn't something that's very neat and tidy. There where we can say, oh, we can solve for this guy completely in terms of that guy. blah, 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 sometimes it comes to us messy and jumbled. But we still want to be able to analyze it from a calculus perspective, talk about rates of change and things of that nature. So we discovered that this is a relationship shared by specific gases, and we might want to know how would the volume change if we change the pressure, right? How fast would the volume react to a change in pressure? Or how fast would the pressure react to a change in volume, right? So I know, let's say we have, like we can do like any random volume. I don't know how you want to measure it, like 5 gallons of this gas that we rapidly compress to 1 gallon. You know, within 5 seconds, how's the pressure going to increase? Let's actually go through the first ones that are far more computational with no context. But the idea is, learning the computations, there is a point to it, because sometimes you never know when it's going to happen. Sometimes you'll need to be able to deal with a relationship that's kind of mixed up and jumbled like this. So let's say I wanted to find y prime here. How do we do that?
Can you take the dy dx of like both
Right.
sides?
Find derivative of everybody. What is this guy?
8x.
This guy.
It's 2y plus 2x y prime.
Right? Need the product rule. So differentiate the x, leave the y alone. Then leave the x, differentiate the y. You get that? This one?
6x y squared plus 3x squared y prime.
Well, the y is
Or
squared.
3x squared.
Right, so that'll still
2y.
be a 6 x squared y prime. This would be a minus sign here because technically you do the product rule in parentheses and the negative sign in front is going to distribute. Derivative of 4 is 0, derivative of 7 is 0, derivative of minus ln x is minus 1 over x. So now I can go through and I can group the y primes. 2x minus 6x squared y. That's it. Minus 1 over x. Then bring everyone over, so we have minus 8x minus 2y minus 6xy squared. That accounts for everyone.
Is it plus 6xy squared? You're adding it over.
Where?
6xy
Yeah, at the
squared.
end, that one.
Plus. Yeah, because we move it over, it's positive. And so now we can solve for y prime. And that might look a little bit annoying because of the complex fraction in the top. We can multiply by x over x. Minus 1 minus 8x squared minus 2xy plus 6x squared y squared over 2x squared minus 6x cubed y. So here we have the derivative in terms of x and y. And using numerical techniques, we can approximate coordinates on this function. We can also approximate what the value of, and once we approximate a coordinate on this function, we can plug that coordinate in here to talk about the approximate slope at that point. Although that one you could solve for y, it's actually quadratic. In B, e to the x plus y squared plus ln of x plus y equals 3. How would we differentiate this? e to the x plus y squared.
That's e to the x plus y squared times
Times
1 plus 2y prime.
This one?
1 plus y prime over x plus y.
So remember, we differentiate an exponential by its derivative of the power times the original function. To differentiate e to the u, it's u prime e to the u. So that's this. And to differentiate log of something, it's u prime over u. So we have that. Now we want to actually solve for the y prime. So we can start to expand parentheses here. So this is e to the x plus y squared plus 2y y prime e to the x plus y squared plus 1 over x plus y plus y prime over x plus y equals 0. So we can group the y primes. And if we group the y primes, we will get 2y e to the x plus y squared and 1 over x plus y. And the other guys we move to the other side, so it's minus e to the x plus y squared minus 1 over x plus y. And again, if you want to clean that up a bit, you could just multiply the top and bottom by x plus y to kind of clear the complex fractions. Let's skip that though. Okay, so I think we've kind of got this down. Sounds like it. So let's just move on quickly so we can talk about the other topic. Boom. So if I wanted to find dv dp, okay, let's see if we understand how to do that particular one. So we're going to differentiate both sides. What would the derivative of this look like? So obviously we're going to apply the product rule here. Seems like a clear thing to do. So we're going to differentiate this, leave that, then differentiate this, leave that. Now when it comes to this, how are we going to do that one? If this is the derivative I want to take.
So instead, when you're doing the v's, wouldn't it be 2v, like for that v squared, wouldn't it be 2v v prime? Like is that what you're asking?
Yeah, like how would I differentiate? Like if you were to write this guy down as a prime, which prime would it be?
V prime.
It'd be the v prime. Right? One thing you have to realize is that x and y are dummy variables, so don't be confused if the variables change. This is like your y, and that is like your x, right? So here it's saying p is the independent variable, v is the dependent variable. So basically, to apply the implicit differentiation, this basically says whenever I differentiate a v function, I have to multiply by its derivative. If I differentiate a p function, it's kind of like the independent variable, so I don't really do anything. Okay? So now they have to take on different roles. Vice versa, if I wanted to find the other one, dp dv, then that means when I differentiate the p's, I need to multiply by the derivative. When I differentiate the v's, I don't. Right? So this notation here is really supposed to emphasize to you who is the independent variable versus the dependent variable. The independent variable is always on the bottom, that's going to be the guy that when you differentiate, you don't really do anything. Whereas if you're differentiating anyone else, you need the chain rule. You have to multiply by the derivative. So that's how you kind of want to think about this, which is another good reason I want to go through an example like this. I don't want you guys to just think in terms of x and y. You should be able to think in terms of any two quantities that are of interest and how one relates to the other. So if we go through, the derivative of this is going to be 1, right? This guy I would think of as 5v to the minus 2. So that would be 1 minus 10v to the minus 3v prime. In other words, just for emphasis, let's write dv dt. Leaving this guy alone. Plus, leaving this guy. Then differentiating that guy, well, that's going to be dv dp equals 0. So whenever I differentiate the v, I multiply it by dv dp because the chain rule takes effect. My p is the independent variable. I want to think of the volume as a function of pressure. So now this is going to be kind of annoying. Pretty much you'd expand and isolate the dv dp. One multiply out, so I get v minus 0.03. This multiply out, I would get minus 10v to the minus 2 dv dp plus 0.3 v to the minus 3 dv dp. Here I would have p plus 5 over v squared dv dp. So I can isolate the dv dp's. And I would have minus 10v to the minus 2 plus 0.3v to the minus 3 plus p plus 5 over v squared. And then I bring the other side to the other side, 0.03 minus v. And so I'll be able to say dv dp which can combine these, I guess. Not particularly interested in doing that one. Hopefully you get the idea. The important thing is just pay attention to who is your independent versus dependent variable. Pretty much, once you know someone is your independent variable, in this case it's the p, that's the guy who when you differentiate you don't really have to do anything. Whereas any other variable that shows up, you have to multiply by its derivative when you're differentiating that particular function because the chain rule. So in all these problems where we found y prime, this was dy dx, someone could ask the question, what is dx dy? And in which case, everything will get flipped. When you differentiate the x terms, you have to multiply by an x prime. Differentiate the y terms, you don't have to do anything. The important thing is, our independent variables and dependent variables might change based on context, but what this notation means should be clear. And this is one of the reasons why the Leibniz notation is very nice to get a handle on, because This one doesn't really tell you who's the independent variable, whereas when someone expresses a derivative this way, you can know, oh, P is the independent variable, everyone else depends on that, and so I would need the chain rule when differentiating them. Okay, let's go.
Yeah,
Yes.
question. How come you would view, like in this situation, you would view it as 5 times v to the minus 2 instead of like doing that quotient rule there?
Oh, well, we discussed before that doing the quotient rule when the top or the bottom is a constant is kind of
Oh, it's just like
overkill.
Yeah, okay.
And students usually run into problems. So I prefer, if the top or bottom is a constant, don't do quotient rule, just rewrite it and do the chain. It wouldn't be wrong to do the quotient rule, but it would just take longer than it has to, and give you more opportunities to make mistakes. So here's the new technique of the day. I want to now talk about the concept of logarithmic differentiation. I would like to motivate this with an example. So, recall, we actually know how to find the derivative of something like a to the x. What was that?
A to the x times ln of a.
A to the x times ln of a. Okay. But what about if someone were to ask you something like this? X to the x. Now that puts you in a very unique position. Right? So for the person who's not paying attention, that might not seem like much difference. But I want you to be aware, this is very different from anything we've differentiated before. The power rule does not apply because the power in this case is not a constant. This rule does not apply because the base is not a constant. With this function, both the base and the numerator and the power are variables. Now, what that basically means is this does not fit any template that we have so far. So this is something new. So here, we're going to do something that is going to help us deal with this guy, despite the fact that we don't have a rule for it explicitly. To make things simple, I'm going to assume x is greater than 0. The negative case can be dealt with separately. But here's what I'm going to do. Set y equals x to the x. And what I'm going to do, I'm going to log both sides. Now what does that allow me to do?
Bring the x down.
I can bring that x down. So the fact that there was a variable in the power was an issue here, but by throwing a log into the mix, powers aren't an issue anymore. Powers now become products. And what I can do now is differentiate implicitly on both sides, which we now know implicit differentiation. Derivative of this, dy prime over y. Derivative of that is the product rule. Differentiate x, leave the ln x, plus leave the x, differentiate the ln. So that gives you ln x plus 1. So this means I can now solve for the y prime by multiplying both sides by y. And the y was x to the x. And that is our derivative. That is the derivative of this function. So way back when we looked at the laws of logarithms, and we realized that logarithms can help us simplify certain operations. They turn powers into products, they turn products into sums, they turn divisions into subtractions, right? Logarithms can do a lot to simplify an already existing function in terms of the complexity of the operations present. Therefore, it turns out that there are times when we might be given a complicated function that we want to analyze with calculus, but the function is complicated in the sense that we don't really have a rule that can figure it out. What we can do instead is find the log of that thing, use the log rules to simplify the situation, and differentiate implicitly. And that way we can figure out the derivative of more complex things like this, where we don't really have a template that fits right on top of it. So now, we actually know how to differentiate x to the x. So this comes in, this is a very useful technique whenever we have powers that we don't know how to deal with, or we have otherwise really complicated things that it would be nice to break them down, as opposed to brute forcing. Even if the rules that we already know does apply, sometimes it's just really annoying to apply them. So, and this was on one of the problems in the review section, I think. So now you know, now you can see how I actually did it. One of the ways, there's going to be another way to do this. So, the above illustrates what we call logarithmic differentiation. Basically, if y equals f of x and f of x is positive, we can find y prime by 1 logging both sides. So you get ln of y equals ln of your f of x. 2, simplifying as necessary, because sometimes this guy here will be very ugly in the beginning, but you can use the laws of logarithms to actually break them down into a lot nicer little parts. 3, differentiating implicitly. This process is called logarithmic differentiation. This technique is useful in certain situations. Say 1, we have powers we don't know how to deal with. 2, we want to avoid complicated applications of more basic rules, like the product rule and quotient rule. So sometimes you might have a problem where you really don't have a rule that applies to that, but you realize if you take the logarithm of the thing, you can simplify it to situations where you do have basic templates that apply. Versus, sometimes technically we could do it using what we already know, but it would be very annoying to do so. So, to follow up with another example, here's an example of something, just to throw it out there, of something that technically we could do with previous techniques, but we probably wouldn't want to. So imagine if someone asks you to find So, suppose someone tell you your function is this guy. And they want you to find y prime. And I could easily make it more complicated by throwing in an e to the x here and an ln x on top of there or whatever. Now, technically, we know how to deal with a guy like that, right? Quotient rule. You'd realize that when you're finding the derivative of the numerator, you'd have to apply the product rule. When you're finding the derivative of this part and that part, you have to apply the chain rule. So you have this. We can deal with it. We have the techniques to do it. But again, a quotient rule with a product rule and applying the chain rule all in one big problem, kind of annoying. And it seems like a recipe for disaster for anyone not on top of their algebra skills. Or even if you are on top of your algebra skills, so at some point a problem just drags on so long, you lose interest and your brain just stops paying attention and goes, ah. However, with a technique like I just showed you, log differentiation, this guy isn't particularly an issue. For one, the radical is here, so I know the x has to be greater than or equal to 0. And so we can assume it's greater than 0, because if your x is equal to 0, that whole function is 0, so we won't have to deal with it. So the only thing, so we can just assume that x is greater than 0. I'm really going to do this for emphasis. Usually when you want to apply log differentiation, you won't have to worry about this. So I'll kind of give you a situation where don't worry about this too much. When log differentiation applies, you'll know it, because it will be something that you wouldn't really want to do without log differentiation. And in that event, just assume that it's something you can take a logarithm of and just run with it. So you can imagine how annoying this would be to do it using previous techniques. And in fact, if you want practice, you can do this using previous techniques. But let's actually look at it using logarithmic differentiation. Here, I can log both sides. Now, what would the right side simplify to?
Of x plus 3 halves ln of x plus y minus 7 ln of 2x plus 1.
Right. Now, if you look at each of these guys individually, easy peasy. So this means that if I can differentiate both sides now, this will give me y prime over y, and over here, this will just become 1 over 2x. This would become 3 over 2x plus 1. Multiply by the derivative of the inside, which is just 1, minus 7 of 2x squared plus 1, and have 4x on top. Super easy. And so now, we can say y prime is going to be equal to y, which is the original function. So it's going to be the square root of x plus 1 to the 3 over 2 over 2x squared plus 1 to the 7th times this whole thing. This guy here is just your y that I multiplied by. And that's the derivative. So that shows you an example of the power of log differentiation. And you can go and try to do this guy with the quotient rule and the power rule and the product rule and the chain rule and all that. And you can compare. And you can imagine like combining these fractions and then multiplying this out, and that huge mess that you get would kind of be what your answer would look like if you were to do the quotient rule directly, and you can kind of imagine how much of a mess that would be. But with log differentiation, that wasn't bad at all, really. By applying the log, it breaks this up into three very simple functions to deal with. Just do u prime over u for everybody, and we're cool. There's an alternative that we like here. Which I believe when I did the solutions for the review, this is what I used. Because sometimes you don't really have the space to kind of set things out this way, so you kind of want a more compact version of applying the log rules. So what you can do is use the exponential to rewrite. So you can kind of do log differentiation in the middle of something else going on, and it's a lot easier to actually express. So you can recall that I can think of some expression, assuming it can be logged, as e to the ln of that expression. That was one of the log rules that we had. And so, example, if someone were to ask me, how would you differentiate x to the x? Right? So yes, we can do log differentiation as I've showed you before, but what I can do, without going over to the side and say, set y equals this, log both sides, simplify, we can kind of do all of that in a self-contained way by just rewriting this in exponential form. Think of this as e raised to the ln of that. And so now I kind of do that differentiation in the power. So what I would have here is this is e to the x over x. And now I just apply the rule for e. So this is like my u. I know to differentiate this is going to be u prime, which by the product rule times e to the u, which is the original function. And I can actually rewrite this as the original function. This is just x to the x. You realize that's the same answer we got before? So this kind of saves you from the situation where you have to go to one side, set y equals this, log both sides, blah, blah, blah. You can kind of do it all in the power of an exponential. And so it's a more self-contained way of applying the log differentiation. Any questions on this? Any questions on log differentiation in general? Okay, so I think we'll stop there. So another technique under our belt. So yeah, so again, the reviews of the solutions are actually posted now. Make sure you can access them. So in terms of the review, the format is going to be your test more or less. But it's gonna be easier on the actual test. I gave you questions that were harder than what you'd be expected to do. So if you get those under control, you should be in tip-top shape. What you can do is you can even swap out, what would be nice for you to do if you want to even do extra practice, is to just swap out all those questions with questions that are more on the level of difficulty as a quiz, and you should be in tip-top shape before tomorrow. So what's happening?